So, good afternoon, everyone. We have an invited researcher, an invited professor in our premises that he's performing a formal visit from this university. Just give me 1 sec. I'm going to introduce him. Yeah, so our invited speaker is Dr. Jorge Bonet Jara, who received a degree of Bachelor in Industrial Engineering, Master in Industrial Engineering with specialization in Electrical Engineering, and his PhD in Engineering and Industrial Production from the Universitat Politècnica de València in 2016, 18, and 23 respectively. So he's a fresh researcher. He's currently an assistant professor in the Department of Electrical Engineering at the same institution, with his main research area being the diagnosis and efficiency estimation of electric motors. He holds the accreditation for tenured lecturer and has over 100 citations on Google Scholar. He is the author of 11 JCR articles, journal articles, in high-impact journals, IEEE transaction, industrial electronics, energy conversion, industry applications, etc., as well as the author of 14 papers in international conferences. He has carried out national and international research stays with renowned professors in the field of diagnostics, and he has also participated in 5 research projects, both regional and national, as well as industry-funded research projects, including 2 collaborative ones carried out with a water supply company, MCSA, FAXA. Right, FAXA. Finally, he holds 1 patent with national protection, currently being extended to the USA and the European Union, in addition to a patent pending national protection. That's the formal CV. One thing that I can share with the audience, most of whom are students that have attended the Advanced Electrical Machines course, is that when I taught you about stator interturn faults, I have shown you a brand new method that worked very well on submersible pumps, water pumps, and that was a product of research collaboration between Dr. Bonet Jara and myself during his visit as a PhD student back in 2022.
Yes, I
That was my first year at the university, and he visited me as a visiting PhD student, and we worked on very interesting stuff at that time with stator faults. So for me, it's a great pleasure to host him in the university today because, well, last time he was here, he was a PhD student, and now he's an assistant professor, so his career is moving forward quite fast. So the floor is yours, and you can start with your presentation. Thank you.
Okay, so thanks Costa for the nice introduction. Okay, so welcome everybody to this technical seminar on electric motor diagnostics, and in particular on speed estimation and signal acquisition with low
Closer to the mic.
Okay, with low noise floor levels for induction motor fault detection. Okay. Well, I'm going to skip that part because Costa's already introduced me, so just a little bit of things. I work in the Institute of Electrical Technology, that this is my research group, where we conduct research, development, and innovation to drive the energy transition. Okay, being one of the main focus, the electrical machines diagnostics. So, as for my particular focus on research, it includes non-invasive diagnostics of induction motors with special emphasis on sensorless speed estimation and signal conditioning, being the ultimate goal enabling reliable fault detection in any industrial application using only non-invasive measurements. So, well, once again, I'm going to skip that part because I've already told you about that. And just here, I want to highlight that the topics covered in my research include the sensorless speed estimation, broken rotor bar detection, eccentricity faults, interturn faults, as Costa already told you, and hopefully in a couple of weeks it will include also bearing detection. Okay? So, where do I apply this research? Well, mainly to induction motors across all industrial sectors, but with a special focus on deep well submersible motors that supply drinking water to communities. Well, so first of all, why diagnose? Okay, here we can take two approaches. Okay, we can conduct a corrective maintenance, that is, react after the fault occurred, which means unplanned downtime, emergency repairs, production losses, and potential safety hazards. So the motor dictates when you stop. Or we can take a different approach, which is predictive maintenance. So we detect incipient faults before they become critical. So we can schedule repairs at convenient times, extend motor lifetime, and avoid catastrophic failure. So it's a way that we can save a lot of money. So keep that in mind. The key is detecting the fault while it is incipient and while the motor can still run. So we can schedule that repair, okay? Well, so what things do we have here? Well, there are a lot of things to diagnose a motor. Here I'm just going to review a few of them. So first of all, we have vibration analysis, that we use it to detect mechanical faults such as bearing damage, unbalance, or misalignment. Okay? For that, we use an accelerometer that we place on the motor housing. Then we have infrared thermography, which allows us to identify hot spots, which can be an indication of overload, interturn force, short circuits, or ventilation problems. Here we need a direct line of vision to the induction machine, of course. Then we have partial discharges, okay, that allow us to monitor the insulation degradation in medium to high voltage machine. It requires specialized and expensive equipment most of the times. Then we also have air gap and stray flux, okay? With the methodology, we measure flux asymmetries caused by faults. Okay? This methodology has some better sensitivity to rotor defects than, for example, another well-known methodology that is MCSA. But it requires a sensor to be installed inside the motor if we are measuring air gap, flux, or on the motor housing if we are measuring stray flux. And finally, we have one of the most famous ones, which is MCSA, that analyzes the stator current to detect electrical and mechanical faults. The main characteristic is that it's fully non-invasive. You only need a clamp like this one, okay? You clamp it just on the cable that fits the motor, and that's all, okay? It's one of the less invasive methodologies that exist. Well, now just a quick comparison between the techniques. So, in vibration, we have a moderate invasiveness because we need to access the motor housing to place the sensor. The cost is very low, and sensors are not that expensive, and we cover mechanical faults. With thermography, the invasiveness is maybe lower, but the cost is higher because of the equipment, and we cover thermal and insulation faults. Then with partial discharges, the invasiveness is moderate, the cost is higher, and we are covering insulation faults in medium to high voltage machines. And then in flux analysis, once again, the invasiveness is moderate. We need to reach the motor to place the sensor in the housing or inside the motor. The cost is low. In the end of the day, it's just a coil, okay? And the fault coverage is electrical and mechanical with high sensitivity. And finally, we have MCSA, where the invasiveness is absolutely not invasive. The cost can be very low if you custom design your sensors, and the fault coverage is electrical and mechanical. So MCSA stands out for its applicability, okay? But is it free of limitations? Okay, let's see. MCSA is very prone to false positives, okay? A false positive is when we say that a motor is faulty when it's not. And that can be caused by several reasons. Rotor attacks, rotor magnetic anisotropy, low frequency load oscillations, etc. But it is also prone to false negative. That is to say that a motor is healthy when in reality is faulty. And that can be caused, for example, because you have non-adjacent broken bars, load variation during measurement, and incorrect speed estimation, etc. Well, many of these problems can be solved if we perform a transient analysis of the startup, or we conduct a continuous monitoring. That is, to take measurements of the motor with a short period of time between them. However, in any case, there are inherent limitations of MCSA. And as additional issues, we also have low sensitivity at higher frequencies because the stator winding and the rotor winding acts as a low pass filter. So it's more difficult to detect eccentricity and bearing faults. So, yeah. Okay, perfect. So, at this moment, maybe you are wondering, so why we need to use MCSA if it has all these problems? So, let me put just 2 examples. First of all, deep well submersible motors. In this application, the motors are submerged tens of hundreds of meters underground. So it is impossible to access the motor housing to place an accelerometer or a flux sensor. And of course, we don't have a direct line of vision to apply thermography. Okay, so it's not possible to apply those methodologies here. And also motors that work in explosive atmospheres. So motors operating in hazardous environments where installing additional sensor or opening the motor housing is not permitted for safety reasons. For all these types of applications, MCSA is the only viable option. Okay? So despite its known limitations, MCSA remains the only diagnostic technique that can be applied when the motor is completely inaccessible. So once again, we take the current clamp, we place it on the electrical panel, which is always or usually far from the motor, and that's it. Okay? So it's the only option we have when we have applications like that, despite it has its limitations as we have seen before. So this is why improving MCSA reliability is critical, and that's what this seminar is about. Okay? So first of all, we have talked a bit about MCSA, but what is exactly MCSA? Well, MCSA stands for Motor Current Signature Analysis, and it exploits a fundamental principle. Any fault in an electric motor creates an asymmetry in the magnetic field, which induces voltage component at characteristic frequencies in the stator winding. So these characteristic frequencies appears as a sideband of the spectrum. So each fault type has its own frequency signature that depends on the motor constructive parameters and the rotational speed. For example, here you have the frequency signature of the broken rotor bar. So when you have a broken rotor bar, 2 sidebands appear respect to the fundamental component. So let's see an example. Let's say we have an induction motor with a broken bar. Then we measure a current, we apply the FFT, and what we will see is something like this. Okay? The highest peak in the spectrum will be the fundamental component, and next to it, 2 sidebands will appear. One is when we take the negative sign here, the other when we take the positive sign. So those are the signatures of the fault. Well, so what is the pipeline in the MCSA process? So first of all, we need to acquire the signal. We have a continuous analog signal that we need to transfer into a digital one to analyze it. Okay, for that we need the current clamp and an ADC. Okay, another digital converter. Then we need to apply some preprocessing, okay, filtering, windowing. Then the spectral analysis, we apply the FFT and obtain the frequency domain. And once we have the frequency domain, we have to perform the harmonic detection, that is to identify the fault signature. Once we have the fault signature, we can compute its amplitude and provide a diagnosis. So the harmonic detection is a critical stage. It requires low noise and accurate speed estimation. So don't get me wrong here. Diagnosis is equally or even more important than the detection. But if you don't have a reliable detection, you will never be able to provide a reliable diagnosis. So for me, this is the bottleneck of the process, the harmonic detection. And here are 2 factors that plays a key role. First of all is the speed estimation. So fault frequencies are a function of the rotor speed. So without an accurate speed estimate, you don't know where to look in the spectrum. Okay? You need to know the speed, to know the frequency, to know exactly where is your fault signature. So even a small speed error can shift the expected fault frequency and lead you to a wrong diagnosis. And the other one is the signal noise. Okay? Fault harmonics are usually way below the fundamental component in terms of amplitude. So the fundamental component has a very high amplitude and the fault harmonics is very low. So if the noise floor is too high, it will vary these signatures and the harmonics will become undetectable. So the higher the signal to noise ratio, the better the detectability. So just to keep in mind, low noise means better visibility of all harmonics. Okay, that's it. A key takeaway. Low noise, better visibility, and that's what we want. So in this seminar, we will focus on these two challenges, okay? Sensorless speed estimation and signal conditioning for low noise. First of all, let me show you the difference speed accuracy makes. Okay, once again, using a spectrum I created here. So, this is a fictitious spectrum, okay? So we have the fundamental component, the highest speed in the spectrum. And then we have two harmonics. One that is a full harmonic, it can be, for example, a broken back harmonic, and another one that's not related to a fault. It can be caused, for example, by low oscillations, okay? So if we have an accurate speed, the search window, okay, the search window here, targets the correct frequency. Okay, so the fault frequency is correctly identified despite a nearby null component. However, if we don't have a precise estimation of the speed, we can think that the fault harmonic is that of here, okay? Because the expected frequency has moved, we consider that that is where the broken harmonic should be, but in fact what we have here is just a non-fault related harmonic. So we can provide a wrong diagnosis based on that information. So super important that accurate speed estimation. Okay, just a reminder, okay? Intense spectra, as the one you will have in real industrial conditions on or when the motor is fed with a variable frequency drive, even a fraction of hertz can make the difference between a good or wrong diagnosis. And I will show you a real example of that. Okay, now the difference noise makes. Okay? So for that, let me change to that mode. Maybe you can see it better. Is it better that way or what? Let's try. If not, I will change it. Okay. Anyways. Okay, let's suppose we have a clean acquisition. So we have our fundamental component, the two sidebands, and that of here, okay, is the noise floor. So in this case, the four sidebands stand clearly above the noise floor. So the diagnosis can be reliable. However, okay, let me see for this term. Okay, here, yeah. So now what we have is a noise acquisition. That of here is the noise level, okay? So now the four sidebands that are or below the noise floor. So the diagnosis become unreliable. You don't know exactly what they are. What you only see is noise. The harmonic may be below, but what you are seeing is just that noise floor. So it's super important to acquire a signal with the lowest noise possible. Okay? So next, I will show you how to acquire these clean signals. First of all, the acquisition chains. Once again, we have the current clamp. Okay? With the clamp, we measure current, but the output, okay, is voltage. So we need that output voltage matches the input range of our ADC. And for that, what we need is an amplification stage. Okay? It, for example, is part of that electronic circuit that amplifies the signal. Okay? Then we need an anti-alias filter. Okay? It's also incorporated in this electronic circuit. Now I will show you why this is important. Next, I have the ADC. Can be a 24-bit ADC, but also can be a 16-bit, 12-bit, whatever. Okay? The higher the number of bits, the better. And finally, the signal has been digitalized, and we can apply our FFT. So the design philosophy is every stage is optimized for one goal: to push the noise floor as low as possible so four harmonics become visible. And then it's something that you must take into account always is that the overall noise performance is determined by the worst stage. So a 24-bit data acquisition system is useless if the input signal to that ADC only uses a fraction of its range, or if the aliased noise contaminates the spectrum. We will see this through examples, okay? So first of all, let's talk a bit about the resolution and effective bits. So first of all, the dynamic range, which is the theoretical noise floor. It is given by this formula here that depends on the number of bits. So for a 24-bit ADC, the dynamic range, the theoretical noise floor, is 146 dB. But if the clamp outputs only 1 volt peak, but the ADC range is plus minus 10 volts, we are only using 1/10 of the input range. So the effective bits are reduced. So instead of having 24 bits, our ADC acts as if it had only 21, and we are losing 20 dBs of dynamic range. So it translates into, instead of having a noise floor that low, we will have a noise floor that is 20 dBs above. So, which is not good for our detection, okay? The solution, well, amplify the signal to fill the input range. And for that, we can use this electronic circuit that is an amplifier. Another trick, which is not always possible to perform. So, imagine this is the cable of the motor. Okay, what we can do instead of only one tap, we can take several taps around the clamp. So each tap, we amplify the voltage, the output voltage of the sensor. So we can combine both techniques. The amplifier, the electronic amplifier, and this analog method. Okay, of course, it's not always possible because it's going to depend on how thick is the cable and how big is the hole of the clamp. But whenever possible, it's a trick you can use. Well, so here there is an example. This is a real spectrum from an induction motor fed directly from the line. Okay? Two spectrums. We have frequency on the x-axis, amplitude on the y-axis. Well, the red one is when the input range is only filled with its 7.3%. And green one is when we fill up to 96% of the input range. As you may see here, the noise in the red one is much higher than the noise in the green one. So there are a lot of harmonics here that we can see in the green spectrum, but we cannot see in the red one. So it's super important to fill this input range so the noise is as low as possible. Okay? Next, now let's talk a bit about the anti-aliasing and the sampling rate. Okay? So an anti-aliasing filter, which is also included here, okay, is a low-pass analog filter before the ADC. It removes all the content above the Nyquist frequency. So the Nyquist frequency, we are sampling at 50 kilohertz, Nyquist frequency is half of that frequency, so 25 kilohertz. So without it, the noise falls back into our spectrum and contaminates it. Okay. Let's see this. So, let's suppose that we are sampling at 50 kilohertz, okay? So, Nyquist frequency is 25. So, all the energy that is above 25 kilohertz falls back into my spectrum, and the noise is increased. But if I put an analog filter with a kind of frequency, just the Nyquist frequency, all that energy to the right of the, or above 25 kilohertz, is decimated, and when it falls back into my spectrum, it does with a lower energy. So instead of having a noise floor like that, it goes down. And here you have an example. Red spectrum without anti-aliasing filter, green spectrum with anti-aliasing filter. Once again, the noise floor in the red one is much higher than the noise floor in the green one. So another step that you can notice, to use an anti-aliasing filter. And then it is the oversampling, okay? So let's suppose that the band of interest for you is between 0 and 1 or 2 kilohertz. So in that region are the harmonics you are looking for. So it would be enough to sample at 4 kilohertz, so Nyquist frequency is 2, or 2 kilohertz, so Nyquist frequency is 1. Okay, that would be enough. However, what I always do is to oversample. So instead of sampling at 4 kilohertz, I sample at 50 kilohertz. Why? Well, because in that sense, I have extra aliasing margin. So, let's say that I'm interested in that band, but I'm sampling so that my Nyquist frequency is here. Okay? So, when all that noise above the noise frequency falls back into my spectrum, there's a large number of points where it distributes. So, the overall noise floor goes down. Okay? That is what we call the processing rate. Now let us see a specific example of this. And also because a matter of flexibility, okay? Maybe now you are only interested in harmonics between 0 and 1 kilohertz. But what about if in the future you come up with a new methodology that uses harmonic at 3 kilohertz, 4 kilohertz, and you want to use signal you have already acquired to check that methodology? Well, if you sample only a 4 or 2 kilohertz, you won't be able to do it. But if you have oversampled, you will always be able to do it. Okay? So my recommendation, always do this oversampling. And here, once again, with the spectrum with anti-aliasing filter and without anti-aliasing filter. You can see very clearly here how the noise here is much higher than here. Okay? Well, now let's go to the processing game. So, quick takeaway. More samples, less noise. Okay? So, the number of points of the FFT is what we call the beams of the FFT, and it's equal to the number of samples of our signal divided by 2. More beams, lower noise. And this is easy to understand. So let's suppose that we have what we call a white Gaussian noise. This is a noise whose energy is spread across all the frequencies equally. Okay? So we have a certain amount of energy that is spread about this distance. Okay? So we have a base, and the height is the noise floor. If we increase the base, as the energy is the same, the height has to decrease. So the noise floor decreases. Okay? Let's see this one example, which is easier. Okay, let's suppose that we have a signal like this. It is a sinusoid that has, well, it is a signal that has a sinusoid of 50 Hertz, a sinusoid of 150 Hertz, and a sinusoid of 1000 Hertz. Then we add to that signal a white Gaussian noise of 60 dBs, and then we are going to do two things. First of it, we are going to take only 10,000 samples, which corresponds to 1 second, because we are sampling at 10 kilohertz. And then we are going to take 1 million samples. So more samples, we expect less noise. Okay, let's see this. First of it, the spectrum with 10,000 noise. Okay, we have here the 50 Hertz component. We have here the 850 Hertz component. But where is the 1000 Hertz component? It's not here. It should be here, but it's not. Now let's do some magic and increase to 1 million samples. And magically, the harmonic appears. So it was there, it was here, but it was buried by the noise floor. So it's super important that processing game, okay? Remember, more beams, lower noise, because the noise distributes across a larger number of points. So always important to have this processing game. See here, we weren't able to see the harmonic, but just by increasing the number of samples, we are now able to see it. Well, now I'm going to put everything together and do an equipment comparison, a real one, okay? Two setups. First setup, 16-bit ADC, 75% of the range field, and no anti-aliasing. Second setup, 24-bit ADC, 80% range field, and anti-aliasing. The signal, the line current of a BFD-fed induction motor sample at 50 kHz with a duration of 20 seconds. Here is the full spectrum. See the huge difference we have here. The noise floor, in the case 1, is here. It's almost 80 dBs. In that case, in the green spectrum, the second setup is around minus 150 dBs. So there is a lot of harmonics that what we can see in the green spectrum that we cannot see in the red one because they are below the noise floor. Now let's take a zoom from 0 to 2 kHz more or less, or less, and see how there are a lot of harmonics here that can be seen in the green spectrum but that are below the noise floor in the red one. So the difference, the setup 2 has more bits, and we have used an anti-aliasing filter. Okay? So super important to keep always in mind that the higher the number of bits, the better. Of course, the equipment will be more expensive, but you need to arrive at a compromise. I recommend always a minimum of 12 for sure, and if you can go to 16, if you cannot allow it, go to 24. Okay? Well, and now I'm going to told you about two different things that has nothing to do, or at least are not so related to the noise, which is the windowing and the frequency resolution. So, windowing is a methodology that we apply to a signal, okay? Now let me explain this, okay? The FFT, okay, when we apply the FFT, assumes that the signal is periodic within the capture time. However, when this is not the case, we have what we call spectral leakage. So instead of having a clean thin peak in the spectrum, we have something like this. That is, the harmonic is spreading its energy across a large number of beams. So if I have a low amplitude harmonic here, the energy of the fundamental component will cover it. Okay? To avoid that, we apply a window function, okay, which taper the signal edges to zero, dramatically reducing the leakage. Okay, let's see this. So, let's suppose we have this signal, okay? It starts here, and then we end the recording here. Look at this. At the beginning, the initial value is 0. And in the end, the value is -1. So the FFT assumes that that signal is periodical. So the next point for the FFT is 0. And there is a discontinuity. And that discontinuity is what causes the spectral leakage. How do we avoid that spectral leakage? If we multiply that function by the hand window, for example, there are other windows, but if we multiply by the hand window, what we achieve is a signal that looks like that. And as you can see here, the initial point is 0 as well as the final point. So there is continuity for the FFT. So when the FFT reproduces this periodicity, there is always continuity between the initial point and the last point. So we reduce the spectral leakage. So let's see this with a real example, okay? This is a real motor, okay, that we have measured a couple of weeks ago. First of all, we take the FFT without the window. And apparently, there is nothing wrong with this motor. We just see the fundamental component, but we don't see any sidebands. Okay, for me, now the motor is healthy. However, if I now apply the window, I can clearly see the broken bar harmonics. And in this case, they are above the threshold that we start considering that that motor may have a broken rotor bar. Okay, so it's super important. If I have not applied the hand window, I would consider that motor as healthy, when it's not. So it's always important to apply this window effect, okay? Well, and finally, what I call the final is the frequency resolution. Okay, low noise is not enough. If two peaks are closer together than the resolution, they merge into one single peak. So you cannot know if it is the broken rotor bar harmonic, it is the fundamental component, or another harmonic that has merged into one. What is the frequency resolution? It's the inverse of the capturing time. So if I'm capturing 50 seconds, 1/50 is your frequency resolution. So here what we have is a trade-off. If we want higher resolution, we need higher acquisition time. But higher acquisition time implies speed fluctuations. The motor can change load during the recording, short motor runs, maybe the motor stopped during the recording, or real-time constraint if you want to implement a real-time diagnosis system. Okay, there is always a compromise. However, if we have an accurate knowledge of the speed, we know exactly where to look and we can decide what is the minimum resolution required. Well, once again, let me put you a real example. Okay, this is a real machine from a company in Valencia. I'm sampling only 10 seconds. Apparently, everything is correct. I only see the fundamental component and nothing else. However, if I now increase the frequency resolution, I can clearly see the broken bar harmonics. So in that case, they were so close to the fundamental component that they have merged into one single peak. But when I have sufficient frequency resolution, I can clearly see the three peaks. The broken bar harmonic to the left, the fundamental component, and the broken bar harmonic to the right. Now let's take a look to the upper mixed eccentricity harmonic, which appears in a 2-pole machine, to the left of 100 Hz if we are feeding the motor with 50 Hz. Okay? So if I look at the spectrum with only 10 seconds, what I see here is just a single peak. I don't know if that is the mixed eccentricity harmonic or just a multiple of the fundamental component, a non-related fault. However, if I increase the frequency resolution, now I can clearly see the two peaks, the mixed eccentricity harmonic and the multiple of the fundamental component. So, see, with low frequency resolution, you only see one peak because they merge into one, because they are so close. But if you increase the frequency resolution, you can define perfectly the mixed eccentricity harmonic and next to it the other harmonic, okay? It's always important also to have enough frequency resolution. And now let's go to the block of the speed estimation. Okay, so now I have told you how to acquire those low noise signals. Now let's see how to estimate correctly the speed. So once again, why speed estimation matters? Okay, as I told you before, every pole harmonic, okay, is a function of the rotary fluid. So without accurate speed knowledge, you don't know where to look in the spectrum. In dense spectral regions, as you will find in reality, in industrial environments or when the motor is fed with a variable frequency drive, multiple harmonics coexist very close together. So I need to know very precisely where to look, so that I don't confuse a healthy harmonic with a faulty one. And here you have an example. Again, a real example. Okay, 2-pole motor, 90 kilowatt submersible motor power. So what do we have here? The fundamental component, then 2 sidebands which are related to load oscillation, not a fault, load oscillation, and another sidebands which are related to broken bar faults. So see how close are those sidebands. They are separated 0.1 Hz. That means that only in this motor, only a deviation of 3 revolutions per minute over the 3000 that this motor is rotating can translate into a wrong diagnosis. I mean, they are so close. It's just 0.1 Hz. I could think that the broken rotor bar harmonic is this one instead of that one. Okay? So, super important that accurate speed estimation, just to know exactly where my harmonic is. Well, so, without accurate speed estimation, MCSA can never be reliable. This is unnecessary to no sufficient condition. Why do I say that? Because there are other factors that can affect the reliability of the diagnosis. But if you don't have a reliable speed estimation and therefore a reliable detection, you will never have a reliable diagnosis. Okay? So, what speed estimation method do we have? Of course, physical sensors, an encoder or a tachometer. Okay? So, an encoder requires precise assembly and its cost is proportional to accuracy. Also, it is sensitive to operating conditions, while a handheld tachometer requires the shaft to be accessible. So this is not always possible. Then we can use nameplate data. Okay, we can take the slip current curve and make a linearization. What is the problem? Well, the problem is that at no load, that is at synchronous speed, the current is not zero. We have always a no load current. And that no load current is very high in induction machines. So in a transformer, you don't have an air gap. So the magnetizing current is very low. However, in induction machines, you have an air gap. And the magnetizing current can be very high. In big machines, it is around 20–30% of the rated current. But in small machines, it can arrive up to 90% of the rated current. So you need to estimate that current, which is not easy, okay? And also, apart from that, the name-rated slip has a tolerance of ±20% in motors above 1 kilo. And also, you always have some degradation in the motor. So it's very unreliable to estimate the speed based on nameplate data. So I do not recommend to do that ever, okay? And then we have the sensorless estimation from electrical measurements. Here we have 2 groups, okay? Fundamental model-based methods that depend on time-varying parameters, and magnetic anisotropy-based, which exploit rotor-induced harmonics. Okay? In this case, we don't require physical sensors, understanding a physical sensor as an encoder or a tachometer. What we need is current clamps, and in some cases, also voltage proofs. Okay? Well, Within magnetic anisotropy base, we have two types of family: signal injection, that requires an external supply, and slotting and rotational frequency 7 harmonic, which are my favorite. Okay, those are the ones that I use. Why do I use those? Well, because they only need one current measurement, the same as MCSA. So they are the most compatible one with MCSA. And in addition to that, they do not depend on temperature parameter, they depend on constructive parameters, the number of pole pairs, the number of rotor bars, which are fixed parameters. They do not require an external excitation, they are there regardless of the excitation, and they process speed-dependent harmonics that are already in the spectrum, such as the MCSA. So how it works is the inverse process with MCSA. In MCSA, we need the slit to calculate the frequency and locate the harmonic. To estimate the speed, we locate the frequency, and using the formula, we calculate the speed. Okay, the inverse process. Well, within this family, we have two types of harmonics: rotor slot harmonics and mixed eccentricity harmonics. Rotor slot harmonics are produced by the discrete nature of the squirrel cage, and their frequency depends on the number of rotor bars. The number of rotor bars is a parameter that is rarely known by motor industries. It's not in the nameplate, it's not in the datasheets. So this is what has prevented this methodology to be implemented at industrial scale. However, we conducted an investigation showing that RSA methods can work without knowing the number of rotor bars. And we tested that with 100 industrial motors. So now they can be used, okay? And then we have the mixed eccentricity harmonics, which are caused by rotor stator misalignment, okay, eccentricity. And the frequency depends only on the number of pole pairs. You can always know the number of pole pairs from the nameplate data. So that is the reason why they has been used traditionally in commercial devices. But now there's a key question that arises. So since both techniques can now be implemented at industrial scale, which is more suitable and reliable for automatic MCSA algorithm? Well, we have answered this question in our recent paper, okay, where we have analyzed both harmonics and from 2 points of view, from detectability and accuracy. So what we have done is, we have taken 3 databases, one containing information on more than 3,000 motors. The other one is 100 measurements of industrial motors. The third one is just a battery of signal that we have generated in our lab. And with that, we have studied how easy are those harmonics to detect and how good is the speed estimation. Okay? So just a quick summary of those results. Okay? First of all, we have studied the existence, the probability of existence. So how likely is to find those harmonics in the spectrum? Well, an induction motor only produces rotor slot harmonics of order K if K by R over B is even. So not all motors produce the highest amplitude rotor slot harmonics. So see here, in the formula we have a parameter that is K, okay, that can take several values, 1, 2, 3. So the higher the number of K, the lower the amplitude of the harmonics. So those are the harmonics of K equal to 1, those of K equal to 2, and those of K equal to 3. So what we want is motors that can produce those harmonics of here, which are those of higher amplitude. Then, in the case of mixed eccentricity, the main mixed eccentricity harmonics exist in any machine regardless of the design, as long as there is some degree of eccentricity, which is always the case due to tolerances during manufacture. Okay? However, this does not guarantee that this inherent eccentricity is enough to see the harmonic above the noise floor, but they are produced regardless of the motor design. Well, going back to the rotor slot harmonic, what we have found is that in 70% of the motors of database 1, that is 3,000 motors, they were able to produce rotor slot harmonic of K equal to 1, those of high amplitude. And when we analyze only 1 pole pair machines, it goes up to 98% of the motor. And in 2 pole pairs, it stays in 72. So those are the most common motors in the industry. 1 pole pair, 2 pole pair, then they are not so common to have 3 or 4 pole pair. But they exist, but they are not that common as 1 pole pair that are used a lot in in submersible pumps or tube or burst machine. So in the end the conclusion is you can find rotor load harmonic of sufficient amplitude in almost any induction mode. Okay? Then we have also studied the amplitude and the signal to noise ratio of each harmonic. So we have taken any of the 100 industrial measurements we have, and we have measured the amplitude of the rotor load harmonic and the noise floor around it. And the same with the mixed eccentricity harmonic. So those are the results. Here in the upper figure, blue bars are the rotor load harmonics amplitude and black bars the noise floor. Here in the bottom figure, we have the same but for mixed eccentricity harmonic. So we have two main mixed eccentricity harmonic. What we have done is, okay, first of all, we look what is the highest amplitude harmonic, if the lower or the upper, and then if it's the upper, with the upper one, I see what is the noise floor around. Okay, so the same with the rotor load harmonic. Yes, to record amplitude and noise floor. Okay, and here just the box plots that exploit the statistical information in this graph. But as a conclusion for you, rotor load harmonics has higher amplitude, lower noise floor across all motors. So they are, in theory, easier to detect than mixed eccentricity harmonics. And it makes sense because mixed eccentricity harmonics are very close to the fundamental component. So the energy of the fundamental component is spread and it affects the noise floor level around the mixed eccentricity harmonic. However, rotor load harmonics appears maybe at 600 Hz, 1000 Hz, 2000 Hz, where the noise floor is very low. Okay? Then we have also studied what we call dominance. So, for you to know, in any automatic sensor versus speed estimation algorithm, we detect the highest peak in a surge band. That surge band is defined by the sleep at no load, that is zero sleep, and the sleep at rated load. Okay? So that is the surge band. Well, dominance measures whether the target harmonic, rotor load harmonic or mixed eccentric harmonic, is actually the highest peak. So total dominance, it is the highest. Partial dominance, a higher harmonic exists, but is at the edges of the band, so we can narrow the band and avoid it, and no dominance. And here are the results. What we have found is that in 76% of the cases, the rotor load harmonics presents total dominance. And in the case of mixed eccentricity harmonic, only in 55%. Okay? If we now compute together total plus partial, we have 90% of the cases with rotor load harmonics and 83 with mixed eccentricity harmonic. So, once again, the rotor load harmonic outperforms the mixed eccentricity harmonic in this criteria. In addition, rotor load harmonic dominance problems are easy to deal with because in the case of mixed eccentricity, you only have two harmonics, but rotor load harmonic, you have multiple of them that are linked to nu equal to 1, nu equal to minus 1, nu equal to 3, etc. And in addition, the bandwidth of the rotor load harmonic is much higher than that of the mixed eccentricity harmonic. What is the bandwidth? The bandwidth is how much the rotor load harmonic can move from no load to full load. Okay? So that bandwidth is much bigger than in the case of the mixed eccentricity harmonic. What means? If I narrow the bandwidth, I'm only leaving aside a small number of sleeps, maybe only 0.05 sleeps, 0.005, doesn't matter. However, if my bandwidth is narrow, as is the case of eccentric harmonic, if I narrow it a bit more, I'm leaving a lot higher sleeps aside. Okay, for example, maybe 1 sleep, 1% sleep, 2% sleep, and there are some motors that I will not be able to estimate the sleep. And finally, what we have studied also is the load dependency. Okay, I want a harmonic whose highest amplitude is at higher loads. But because at higher load is where most industrial motors operate. And what I have found is that most rotor load harmonics, or there are several of them, that has its highest amplitude at higher loads. While in the case of the mixed eccentricity harmonic, as I increase the load, the amplitude decreases. So, in summary, rotor load harmonics are easier to detect exactly where most industrial motors operate, which is what we want. See? if the mixed eccentricity harmonic is, when it's more detectable, is at low loads, there is a problem. Because at low load, there are few motors operating at low loads. Majority of them operate maybe between 60 to 100% of the rated current. Well, and finally, what we have studied as well is the accuracy of the speed estimation. Okay? Very easy here. We have estimated the speed through the rotary load harmonic, through the mixed eccentricity harmonic, and we have compared it with a high precision encoder. Okay? In several conditions, different slips and different supply frequency. And what we have found is that the rotary load harmonics are generally much more accurate than mixed eccentricity harmonics. There are only 2 cases where the mixed eccentricity harmonic exceeds the accuracy of the rotary load harmonic. And that is when the motor is fed from the grid with very low load. Why? Well, in that case, we have a lot of slip frequency stability. That is, the rotary load harmonic is moving a lot. So the highest peak, okay, which is marked here, the highest peak do not match the average speed. So there is a big error. However, if that same motor is fed with a variable frequency drive, we reduce a lot the slip frequency stabilities, and now the peak is a clear thin line. So the average speed matches the highest amplitude of that harmonic. So, as a conclusion, rotary load harmonics provide up to 16 times more accurate speed estimation in most operating conditions. And finally, we have also studied the diagnosis reliability. So what we have done here is easy. So the broken bar harmonic is not a thin line. It's something like that. Okay, so we have gone spectrum through spectrum, recording the maximum amplitude of that harmonic, just in the peak. And then what we have done is, okay, we take the rotary load harmonic, estimate the speed, with that speed we compute the frequency, and we see what is the amplitude at that exact frequency. Maybe the amplitude, the real amplitude is here, and with my frequency, I'm here. So there is a bit of error, okay? So we have computed how much is that error, and in how many cases you have that error. So, those are the results. What we have found is that rotary load harmonics gives error always below 4 dB, and below 2 dB in 91 to 100% of the cases. So they are much more reliable than mixed eccentricity harmonic to perform diagnosis. So, conclusions and takeaways. Well, regarding signal acquisition, remember, you need a carefully designed acquisition chains, a 24 data acquisition system, an amplifier, an anti-aliasing, a high sampling rate, and long gap. All that is essential to boost the noise as low as possible and make the 4 harmonics visible in the spectrum. And then, regarding the speed estimation, estimate the speed through the rotary load harmonic is the best option you have, okay? Because they outperform mixed eccentricity harmonic in every criteria we have studied, and because they are the most compatible one with MCSA. It's just the same process. We measure one current, we analyze the spectrum. So, together, low noise acquisition and accurate sensor speed estimation through rotary load harmonics enables a reliable, non-invasive motor diagnostics via MCSA in any application. So, thank you very much, Evharistopoli, and now I'll be glad to take any question from you if you have any.
Right, thank you very much for your presentation, for keeping the less than 1 hour slot that I gave you. Can you please mute yourself?
Okay.
Yeah. Does anyone have a question for you? Yeah, go ahead.
Okay, I wanted to ask, in the, I think, 17th slide, you showed...
17.
Yeah, I think. Showed the diagrams.
Sorry, unmute yourself. I was ready to say something, but so that people online can hear your answer. Because he doesn't have a microphone.
Okay.
Yeah.
Good. You showed the diagrams when sampling with 150 and 1000.
Yeah,
something.
it's that one.
Yeah. How come that we lose the third harmonic when sampling with a few samples, when the noise is generally lower than the harmonic?
Well, here what's happening is that in both cases, the noise is the same. It's the same energy. In the first case, we have less samples. Okay, so that energy is distributed across a narrow base. So the height is higher. If now increase the base by increasing the number of samples, as the energy has to be the same, the height has to descend. So the noise floor descends. And that is what we see. As the noise floor descends, the harmonic emerges.
Okay. So it's not that we don't get the sample from the first one, it's that we distribute better.
Yeah, exactly. I mean, in the first one, the harmonic is there. The only thing is you cannot see it, but it's there. It's below the noise floor.
Okay.
So what we do is increase the base, so the noise has to go down.
Okay.
Because it's the same energy in one spectrum than in the other. But in the second one, that energy is spread across all the spectrum, so the noise goes down.
Okay, okay.
Any other question? Well, I have comments, not really questions. I have 4 of them. First one is that thermography can be used for mechanical faults as well.
Okay. Yeah.
Because if you have a mechanical fault, it will lead to friction.
Yes, of
and
course.
friction generates heat.
Yes,
and also it's from the outside of the machine, usually at the end. So it's very easy to pick with thermography.
Yeah.
The second thing is that mixed eccentricity. Okay, from your results, you are proving that mixed eccentricity has a lot of mathematical disadvantages as a harmonic to be used for speed estimation. Okay. However, in large machines, the bigger the size, the more difficult it is to predict the number of the bars accurately, because you have more design options.
Yeah.
And I have seen motors in the same size, let's say 2-3 megawatt, and one motor has more than 100 slots, and the other has 80 or 70. So this is a very big difference that can, through that, you can make a serious error in the estimation of the speed.
But in the methodology we developed, we are not using any kind of statistical information to ascertain what is the probable number of rotor bars.
Statistical means that there are statistical outliers as well, and you can make a mistake.
Yeah, but we are not using statistical information.
Okay.
We are analyzing the whole spectrum and seeing a series of patterns that allow us to determine which are the number of rotor bars of that specific motor. So
but what if a company changes the number of bars by 2? The difference is very small, or 4. So you have a motor with 100 slots and a motor with 104 slots. So the PSH or the RSH is just slightly shifted left and right.
Yeah, well, we have tested that with 100 motors, and we have seen that we are able to see those differences. So we can know exactly how many are the rotor bars in every different induction machine.
Okay. Well, I was going to say that the most reliable is by far mixed eccentricity mathematically, because it doesn't depend on anything.
Yeah, of course.
But the main disadvantage is that in large machines made from copper, I don't know if you had some of those in your study. Did you have big machines or just?
No, yes, I have a couple of big ones, above 500 kilowatts, and also some of 1 megawatt or something like that.
You had some of those. Okay. If you have machines from copper, well, in those, the mixed eccentricity is usually absent.
Yes.
You don't see.
Yeah, I see that.
So we rely on the mixed eccentricity for small motors, not for large ones. But large ones are the ones that will invite you to diagnose and pay you.
Exactly.
Small machines, no one's going to
exactly.
pay you for diagnosing. The other one is just an addition to what you said, and maybe you want to adopt that when you make the same lecture again. That RSH, they naturally exist in the machine because they are a design characteristic of the machine. They are there because they express the main magnetic field of the rotor. And so they take into account the phases of the rotor, which is the number of the bars, correct? So the opposite is for eccentric machines. And that's why the amplitude is so much higher than the noise floor because they are supposed to be there. The last thing about that is that because you said that in many machines they operate close to at high loads.
Yeah, more or less what I've seen is between 60 to 100% because there is always oversizing of the machine.
Yeah, exactly. So that's a critical thing because oversizing is a very strange term around motor engineers. Because yeah, if you are, let's say, up to 50% loading below the nominal condition, then that's fine. You're not going to see a big difference anyway. But there are a lot of motors that have no load operation or low load operation where saturation is very high.
Yeah.
And in those cases, mixed eccentricity harmonics, they are amazing for estimating this.
Yeah, absolutely. This is the case.
Especially in big machines.
Yes.
Because you saturate them. You saturate the rotor.
Yeah, that's what we have seen, that the lower the load, the higher the amplitude of the mixed eccentricity harmonics.
Yeah. And in large machines, where mixed eccentricity is impossible, many times it's impossible to detect at steady state. If you are at low load, you might be able to see something.
Yeah, absolutely.
Yeah. So that's all from me. But just consider adding those few elements. Yeah. And the thermography.
Yeah, for sure.
Because I think Antonino and the guys from Mexico, I think they published a paper at some point where broken bars, they couldn't see anything with thermography. But misalignment, loose belt, bearing faults, all that stuff.
Yeah, because of the friction.
Yeah, because of the friction. They could generate very unique thermal image.
Okay.
Yeah. By the way, thank you very much because that presentation, they have exams in a few days on diagnostics. A part of the curriculum is diagnostics, and I think that was the best revision they could have because we started with diagnostics at the beginning of the semester.
Okay, nice.
What was it? Revision, So, are there any other questions? No. Okay. Well, thank you very much for your time.